Okay, let's dive right into this. You know, when most of us think about Bitcoin, we think about digital money, right? Finance. But what if I told you that hidden deep inside its code is this powerful feature for storing, well, for storing data? It's a capability that goes way beyond just money, letting the blockchain act as a permanent, unchangeable public record book for pretty much anything.
And that brings up a really fascinating question. Can Bitcoin's blockchain really be used for more than just sending money around? It seems like a simple question, but believe me, the answer to this completely changed how developers started thinking about the future of this entire technology. And the answer is a resounding yes. But it wasn't some simple, clean upgrade. The first attempts to make this happen created a huge, unforeseen problem. It was like a kind of technical debt that actually threatened the efficiency of the entire Bitcoin network. This powerful idea was also a really dangerous one.
So this brings us to what we can call the blockchain's data dilemma. On one hand, you had developers who were incredibly excited about Bitcoin's ledger. I mean, it's immutable, it's time-stamped, anything you put on there is there forever with a verifiable date. That is a dream come true for things like proving a document existed or registering a copyright. But cramming that data in, well, that created a real peril.
And that peril has a name: blockchain bloat. The first methods for storing data were, to be honest, just hacks. They were clunky workarounds that left behind a permanent mess for every single computer, every node, running the Bitcoin software. To really understand why, we need to pop the hood and look at a critical part of Bitcoin's engine.
And that component is called the UTXO set. The easiest way to think about it is like a super fast global database that only tracks unspent Bitcoin. It's the thing that every computer on the network has to keep in its active memory to quickly check if new transactions are valid. So for Bitcoin to stay fast and efficient, this UTXO set needs to be kept as clean and as small as possible.
And right here, you can see the problem in action. A normal transaction is clean. It just spends some digital change and creates new digital change. Simple. But the old, hacky way of storing data was to hide it inside these fake outputs that could never actually be spent. This created permanent digital junk, just clogging up that critical database with IOUs that would never, ever be claimed.
So the network was getting bogged down with all this permanent bloat, and it desperately needed a real fix. This is where OPR return enters the picture. And it wasn't another hack or some clumsy workaround. It was an elegant, purpose-built solution designed specifically to solve this problem.
So what is it exactly? Well, OP_return is a special command, an opcode, that lets you create a transaction output that is provably unspendable. It's basically a way of shouting to the entire network, hey everyone, this little piece of the transaction, it just contains data. You can officially ignore it for spending purposes forever. This one simple instruction changes absolutely everything.
And the process itself is wonderfully simple. You just create a regular transaction, but in one of the outputs, you stick the OP_return command followed by your little piece of data. Because the network instantly recognizes this output as unspendable, it can be safely pruned or just removed from that critical high-speed UTXO database. So the data is still stored on the blockchain forever, but it doesn't create that nasty bloat. It's truly the best of both worlds.
Now, this solution has three huge benefits. The first one is that it's explicit. There's no guesswork. A node sees OP_return, and it knows without a doubt that this output is just for data and can never ever be spent.
Second, and this is the absolute key, it's prunable. Since the output is explicitly unspendable, nodes don't have to waste their precious active memory tracking it. This one feature directly attacks and solves the blockchain bloat problem that was plaguing the network. And finally, it's standard. OP_return created a single, officially recognized way to store data on-chain. This basically ended the Wild West era of messy, custom workarounds and brought some much-needed order and clarity to the whole process.
Okay, so that's the theory. But how is this elegant little tool actually being used out there in the real world? Let's take a look at OP_return in the wild, because this is where it gets really interesting.
The use cases are really practical and pretty fascinating. People are using it for notarization, creating a permanent mathematical proof that a certain document existed at a certain time. It's being used for issuing digital certificates, for time-stamping software releases, and even for academics to register a thesis, creating an immutable record of their work.
So how does this actually work? I mean, you're not storing the whole document on the blockchain, right? No way. Instead, what you do is you create a cryptographic hash. Think of it like a unique digital fingerprint of your file. Then you just embed that tiny little hash into an OPR return transaction, and boom, you now have absolute, unchangeable proof that your specific document existed at that exact moment in time.
Of course, no technology is perfect. OPR-ATR is incredibly powerful, but it comes with some very important rules and trade-offs that you really have to understand before you use it.
The first big rule is this number, 40 bytes. That's the default data limit for a standard OP_return output. Now, that might seem tiny, but it's a very deliberate choice. It's just big enough for things like a document hash, but it's small enough to stop people from trying to store, entire movies on the blockchain and abusing the system. It forces you to be efficient.
And this brings us to the big trade-offs, which are really two sides of the same coin. First, there's a cost. You have to pay a transaction fee, which creates a natural market for this limited resource. Second, it is completely transparent. Anyone can see the data you post, which is great for public verification, but obviously terrible for privacy. And finally, it's permanent. Your record is tamper-proof forever, which also means you can never, ever delete or change it.
So where does that leave OP_return today? Well, it remains an absolutely fundamental tool, and it has this lasting legacy as a truly elegant solution to a really complex problem. At the end of the day, while newer, maybe more complex ways to store data have popped up on other layers and sidechains, OP_return is still the fundamental, built-in standard for putting small, public, time-stamped data directly onto Bitcoin's main chain.
It really makes you think, doesn't it? OPR return was a brilliantly simple fix for a very big, very messy problem. It's a great reminder that sometimes the most elegant solutions are not the most complex ones. And that kind of leaves us with one final question to ponder. In a world that's only getting more complex, what will the next simple, elegant solution look like?